Today we're going to tell a little story called The Parable of the Marble and the Block, narrated by Miss Laviniac. One lazy afternoon, there was a block, standing tall and strong and motionless at the edge of a table. I'm denoting the center of mass of the block for future use. Let's assume the block is uniform, has length L, has mass M, and is initially at rest. All of a sudden, out of nowhere, comes a sinister marble. That marble is moving towards the block horizontally at a speed v1, and let's also note that the marble has mass m1, or m. Let's assume also that the height at which the marble strikes the block is a distance r below its center of mass. What happens, you might ask? What is the fate of the block and the fate of the marble? What quantities are conserved? Which ones are not? How do I approach such a complex problem? Today we're going to answer that question. Okay. In order to make sense of this bizarre situation, we must first consider a few different stages which can help the mind process what it's seeing. Let's imagine our block immediately after the collision, and let's imagine our bullet just after it strikes the block. Oh, it's not a bullet, it's a marble, but it is sinister. Let's assume that the marble recoils backwards, which is an assumption, at velocity v1 prime, in the same direction and at the same height at which it came in. Let's also assume that the block starts to translate forward with velocity v2 at its center of mass, while at the same time begins rotation around its center of mass axis. You probably can work out which way the block will rotate based on how far below, based on the fact that the marble is striking it below the center of mass, but if not, convince yourself that the rotation of the block will be in the counterclockwise direction about its center of mass. Just to play this forward into the future, I'm going to draw this a little while away, so you can see a little bit more clearly what's happening. We have our block still moving forward with velocity v2, while it's also rotating with angular velocity omega about its center of mass, and in the meantime, we have our marble leaving the scene at velocity v1 prime. Let's take a look at situation A, situation B, because they're a little easier to analyze than going all the way to situation C. And let's also assume, for simplicity's sake, so that we don't worry about any changes in speed of the marble, that situation A now involves the moment immediately before the collision. When you hear collision, you think conservation laws, and momentum is one of the quantities that's always conserved in a collision, and that is no exception here. Let's see how the fate of our fair block and sinister marble play out. Let's start with linear momentum, because we know that's conserved in all collisions as long as no external forces act, and this is indeed a system where no external forces act. Let's write the translational momentum of the system in situation A just immediately before the collision. Let's start with the block because it's easiest. It has no momentum. And our bullet has what we know is its familiar expression for momentum, mv1. After the collision, even though things look far more complicated, from a translational perspective, they really are not. We have a block, mass m, moving at velocity v2 to the right, and that velocity we'll assume is positive. And we have our marble, mass m, moving at velocity v1 prime, and v1 prime, with our assumptions we've made here, will be a negative number. But I won't include the negative here. I will assume it's embedded in the value of v1 prime. So we have mv1 equals capital mv2 plus mv1 prime, which is what we would expect from our familiar friend, momentum conservation. Now let's venture a little more into the world of the less familiar and analyze the angular momentum of this system moving from situation A to situation B. Remember, angular momentum can be defined for a particle that's moving relative to an axis or for a rigid object rotating about that same axis. For simplicity's sake, let's put our axis at the center of mass of the block. Now we can define the initial momentum of the marble relative to that point, and we can define the final momentum of the marble as well as the rotation of the block relative to that very same point. Since there are no external torques on the system, which you should take a few minutes and pause this video to convince yourself of if you don't see that, we know that the angular momentum before and after should be conserved. Now we have to remind ourselves how to calculate the angular momentum for all of these different situations. But before we do that, let's just remind ourselves what constitutes the different terms in the angular momentum. We have the angular momentum of the marble, and there's no angular momentum initially in the block. And that's L of the marble initially. Then we'll have the angular momentum of the marble final relative to that same center of mass axis of the block, plus the angular momentum of the block. Let's figure out all these terms. So to calculate the angular momentum, I'm going to do that actually over here of, say I have an axis, an object moving at velocity v, a distance r from an axis. Remember, we use the expression L equals r cross mv. To see the direction of the cross product, we have to reposition our vectors like this so that they emanate from the same axis, and then imagine curling r into v. And if you do that with your right hand, you should see that your thumb points up out of the page. And so the angular momentum here is out. Its value is given by mvr perpendicular, and since they are already perpendicular, it's just mvr. And the direction is out, which we'll call positive. Rotations in the counterclockwise directions, or angular momenta, where you curl the r into v in a counterclockwise way, we'll call positive. Now we can come back to situation B and write our angular momentum before and after. Our initial angular momentum of the ball is just going to be m times v1 times r plus 0 for the block. Our final angular momentum for the ball before it's moved too far, but even after it's moved, because remember, we only care here about the perpendicular component of the radius, is equal to m v1 prime times r plus the angular momentum of the block, which we can write using its moment of inertia and the angular velocity around its center of mass. And that moment of inertia needs to also be calculated around its center of mass. This is the second equation for conservation of angular momentum, and depending on what values are given, you should be able to use both of these to determine the quantities that you want to find. We're actually going to use these relationships to perform a lab experiment by analyzing a video of this exact situation. You'll be able to measure the incoming velocity of the marble, the outgoing velocity of the block, and the outgoing velocity of the bullet just by counting frames and measuring distances. Oh, it's not a bullet, it's a marble. I don't know why I keep saying that. And you'll also be able to measure the rotation rate of the block by watching it rotate and counting as measuring how much time it takes to make one full rotation. You'll be able to measure with rulers that are on the video the radius at which the distance below the center of mass at which the marble actually strikes the block, and you'll have the dimensions of the block to be able to calculate its moment of inertia. One thing to keep in mind, which will also be in the lab, is that we know how to calculate the moment of inertia of a rod about its center of mass. That's just 1/12 ml squared. When you actually have a block with finite thickness, and it's rotating about an axis, wrong axis. When you actually have a block, and it's rotating about an axis through its center, the moment of inertia, if this side is A and this shorter side is B, I is 1/12 a squared plus b squared, which is pretty close if the block is thin to just 1/12 ml squared, but this tiny little bit will be important in this lab. Okay, so now that you've got all that, you've got all the basic theory, you're going to get going, analyze a video, make a spreadsheet of data, and verify that linear momentum and angular momentum are both conserved.